Hey folks, all right, now we know how to calculate that linear regression equation. We know how to calculate the standardized beta weight, right? The standardized slope. We didn't really talk much about how to calculate the r squared error, right, or measure of effect size. So I want to talk about that a little bit more. So let's start with that, and then we'll end this short video with a discussion of how you can use sort of multiple variables at once in a more complicated regression equation, right? Right now we're only using the two, but you could theoretically use 4, 5, 6, 7, or infinite numbers of variables to make an even more accurate prediction. So we'll get to that. It's called multiple regression. Coefficient of determination, right? However you want to call it, proportion of variance accounted for, the standard error, estimate of the error, right? Any of these terms all basically mean the same thing. It's how large of an effect do you have between these two variables? And by, I guess, the flip side of that coin, how much is not being explained, and thus what's the error still associated with this relationship, right, or with this prediction. Excuse me. So the formula we use to calculate the coefficient of determination, you can see on the right side of the screen there, r squared is equal to, and the numerator then, sum of squares total minus sum of squares error, divided by this other concept, sum of squares total again. Okay, so functionally what that equation does is partial out the error and sees what's left, right, from a mathematical standpoint. So we need to figure out how to calculate sum of squares total and sum of squares error. So the sum of squares total can be thought of as all the error that you would have in this experiment, or in this prediction, I should say, if you only use the mean to predict. So we go back to my example. Remember I said that we were correlating absences and exam grades, and I might have a student that comes up to me and says, hey, I'm going to miss 4 days. Well, one response to him is to simply say, well, the average last year was this. You're probably going to get close to that. A better response would be to use the relationship between absences and exam grades that I've seen in past data and use a regression equation to then predict, right? Plug in his value of absences as X, solve for a predicted Y, and potentially get a more accurate prediction. This measure is what we would have, the total error we would have if we didn't do that and we only use the mean. So if you look at what it's doing, it's basically saying, what are all these Y values, right? In this case, grades, because absences was our X variable. What are all these Y values? Subtract off the mean of Y, and let's just get the total deviation between Y and the average, right? And that'll basically tell us how much error there is between using the average to make a prediction when all these individual Y scores differed from it by some amount, right? Say a sum of squares total. And it's a squares, so we take Y, we subtract off the mean of Y, right? It's almost like the first bit is in fact identical to the first part of a standard deviation or variance calculation. You're just creating a sum of squares, okay? So Y minus the mean of Y, you get all of those deviation scores, all those errors, then you square all of those errors, right? Just like before, and then we sum all of those up to get a sum of squares total, right? Graphically, it would look like this, right? You'd have this distance between each of these points on the line. Now, the line is not a regression equation, right? So it's not sloped in any particular way because it's not using a relationship. It's just the average. It's constant. It's what we would say if you told me you had 5 absences. It's what I would say if you told me you were going to have 8 absences. I'm just using the mean to make a prediction. And so all these dots are going to be some distance from that mean. We're calculating that error right now, okay? Now what we want to do is see how much more accurate we are if we use the regression equation instead. So now we have to calculate the sum of squares error, okay? Sum of squares error is taken by subtracting not the mean of the Y, but instead the predicted Y value. So now we need the absences information here, right? We need our regression equation here. So we're going to take each of those X values in the column of absences. We're going to plug it into our regression equation, right, into that X spot, and then we're going to solve through all these predicted values of Y. So we have a new column then of predicted values for Y. Now that we have that, we're going to take those predicted values and subtract them from each of the actual Y values, the actual data we had for grades. This will see how close our prediction is to the actual reality of what grades these people had. This then will be calculating a amount of error associated with just using the regression equation. So now we have total error, if we just use the mean, right? We have error if we use the regression equation. Now we just need to partial it out. So sum of squares again, right? Once we square all those errors, we add them up. In this case, graphically, what we're doing is using our regression equation and seeing how far each of the dots are. And what we're going to do is basically compare them and see if we are closer with the regression equation than we are with the mean. Okay, so we just plug these values in, sum of squares total, sum of squares error, divided by sum of squares total, and we get the coefficient of determination. But there's a much easier way to calculate this, okay? R squared equal to sum of squares total minus sum of squares error divided by sum of squares total would require you to do all of those steps calculating sum of squares total and sum of squares error. Some of that you have because you worked on the y minus the mean of y and squared that for part of your regression equation earlier on so you could get standard deviation and things like that. But sum of squares error is a new one. You didn't have to make all of those individual predictions yet, and so you would have had to do all this additional calculation. So is there an easier, simpler, faster, better, perhaps, way of determining this r squared value? Yeah, obviously there is, but you probably already picked up on it. R squared is just r times r, right? Anything squared is that value times itself. And so instead of going through all that massive amount of work calculating sum of squares total and error just to determine r squared, just take your correlation coefficient, we had a negative 0.85, I believe, and square it. Right? It will then become around a 0.6 in that particular case, right? And you have now a measure of effect size, a measure of the error. In this case, it would say that if we had, let's use that example of a 0.6 for r squared, it would say that 60% of the variance in grades is explained solely by absences. Now, the other 40% of that variance is explained by other things, maybe the amount of homework you did or some other variables that might be incorporated in there. Right, so that's really the way we think about this. In other words, you can also say it is 60%, or we've reduced error, I should say, by 60% by using the regression equation instead of just using the mean, which means our regression equation is pretty solid, right? If you can reduce error by 60%, that's a pretty large effect size. Now, what happens when we want to incorporate multiple variables into our regression equation? Not just the two, but a third variable as well. Right? This is one we call multiple regression, and then when we calculate effect size for it, we call that r squared, but we use a capital R in that particular case. So let's say we take our existing data. We have absences, we have exam grades. Now, ideally, we can come up with a third variable that predicts some of the same unique variability in exam grades. So we said 60% of exam grades are explained by absences, 40% is explained by something else. If we can come up with another variable, find it and measure it, right, document it here and quantify it, then we can potentially explain another portion of those exam grades. And the more and more we're able to explain, the better we are able to accurately predict exam grades, right? Reducing that error. Now, in an ideal world, that new variable that you try to incorporate in is what we would call orthogonal, meaning it's entirely independent. It is not capturing some of the same behavior that absences is capturing. So if I were to add in, say, SAT score as opposed to number of homework assignments completed, SAT score seems to be, at least to me, a very sort of independent variable, right? Not in the sense that we have been talking about independent variables, but unique orthogonal variable to absences. That is, whatever it is about me or you that varies between us and leads to these various absences is probably different from what varies between us and leads to differences in SAT score. And so it should be capturing a different part of that variability. That being said, even if it's not fully orthogonal and it captures some of the other variable and only has a slight unique contribution, multiple regression allows you to use all of those variables together into a regression equation to make that unique prediction, right? So how do we do it? Well, there's two different methods. One, you would use if you had really lots and lots of knowledge about it, the sort of theory and the background, and the other is when you don't have a lot of that and you're trying to let the data tell you what relationships exist out there. At the end of the day, we're taking our simple two-dimensional plane where we had a linear regression and we are changing it to three-dimensional, potentially four-dimensional and five-dimensional. I had a class in graduate school where the guy, when he taught it, would say, so far we've talked about variables like this, but now we're going to add a third variable in, so we need one like this. And then he'd say, now we're going to add a fourth variable in, so we need one like this. And by the end of the class, he'd have 7 or 8 pens in his hand trying to indicate that there were so many dimensions that could be incorporated into a regression equation, right? Because each time you incorporate a new variable, you're potentially explaining a little bit more of that variability, and your equation just becomes a little bit longer. It's hard to think in 4 and 5 dimensional space, so we'll just keep it a little bit simple and talk about the concepts at a sort of a superficial level. Hierarchical multiple regression. When you have a really good theory, so you have already read the literature, or you've made a lot of observations, and you are damn sure that absences and SAT scores both contribute to exam grades, and that you believe absences is the stronger contributor to exam grades as opposed to SAT scores. One explains more of the variability in your mind, right, according to theory. Then what you do when you run what's called a hierarchical multiple regression. When you put this data into software, you do it by hand. Few people are going to do this by hand because it is more complicated math. You decide what order to put the variables in. That's important because the variable you enter into the regression equation first is the strongest predictor. It will have the largest effect on that regression equation. And so this is a really good approach if you know the theory. So you know absences is the best predictor, but then we think SAT also should be a good predictor, so we're going to put that in as well, but we're going to put it in second. So hierarchical multiple regression, the researcher themselves determines the order of the variables, right? And they do it based on this really good theory of how they're related. Now, there are some cons to that, insofar as sometimes you don't have a good theory. Maybe it's a brand new research area and we really don't know what's related to it, right? And we do what's almost like a statistical fishing expedition, where we measure a whole bunch of variables and then we use software to tell us what the relationships are. Well, in that case, it's what's called stepwise multiple regression. Stepwise multiple regression will simply look at all the various R-squared values for all of your different correlations that are in there between your 2, 3, 4, 5, 6, 7, 8 variables that you've added in, and it will order them based on the largest significant R-squared, right? So significant, we haven't really talked about a lot of statistical significance yet, but we'll just hang that for later. The important, the statistically significant R-squared goes first, then the next one that's still significant goes second, then the next one that's still significant goes third, until eventually you have no more significant R-squareds that can be included in the equation. Software determines it all for you. You don't have to have theory. It has its own mathematical theory. Now, that's great. One con, however, is that if you have variables that are not orthogonal, right, they're not fully independent, but they have a lot of overlap. However, that other variable might still be important. It might still explain a tiny bit more of that variability, even if it's only a small amount. In stepwise multiple regression, the software is likely to see these two as so overlapping that it will take whichever one is largest. And when it does that, that will make this one no longer significant because it's no longer explaining very much variability. And that one will drop out and not be included in the equation. So sometimes stepwise multiple regression will leave out some variables that might be interesting simply because they make a very small increase in predictive power as opposed to a very large significant one. So hierarchical versus stepwise really is determined based on kind of what you know and how much you feel like you can order those variables in the equation based on theory. Okay, so that wraps it up. That's regression. That's everything. Now, there's one more video here where I'm going to show you start to finish how to calculate correlation and regression, beta weights, R-squared, everything all in one big shebang, right? We have covered a lot. Now, I say a lot. It's really pretty simple stuff. We created a line. You already know how to create lines because we've done linear equations since high school, right? In some cases, middle school, right? All we did was rewrite the equation. So it's not y equals mx plus b, it's now y equals a plus bx, but it's the same thing. It's got slope, it's got y-intercept. Then we had to figure out how to calculate slope and y-intercept. Thankfully, y-intercept's pretty intuitive. It's when x is equal to 0. So we just used that little z-score calculation where we figured out the z when x is equal to 0. Then we used that to get a predicted z of y. Then we used that to get back to a predicted y. And there we go. We had a coordinate 0, comma, y-intercept. We did it again at 1. Subtracted them off for rise over run, and we got slope, right? That was it. We had our equation. Quickly make a standardized beta weight, right? Standardized slope, pretty easy. You just use sum of squares. So again, very easy to calculate. And then we talked a little bit about this sort of what could be a bear of a calculation, creating the standard error of estimate or coefficient of determination or proportion of reduction in error, or proportion of variance accounted for, all the various terms for the same thing, and then realize it's just R squared. So that's easy. And then lastly, we wrapped up with a little discussion of multiple regression and what we do when we have lots of variables in our regression equation. So take a break, get some coffee, and buckle in for a long calculation example now. Okay? Cheers.